So this exercise related to the space physics. We did the first 3 questions from this exercise. So moving on to question 4, this question is about the planet in the solar system. So you can see the representation. Planets in the solar system have different size and masses. The bar chart, which shows the gravitational field strength of each planet compared to that of Earth. So Earth, why it's like it's a comparison, it's a relative. Which of these statement is correct? If the planet gravitational field is stronger, it means the weight will be more. So which statement is correct? You can use the screen annotation to mark which one you think is the right statement. The gravitational field strength are given. The bar chart is showing the relative gravitational field strength. Which of these statements is correct? The statement B is the right one. How we identify 1 kilogram mass would weigh more on Earth than on Uranus. The reason is that because when you compare the gravitational field strength of the Earth with the gravitational field strength of the Uranus, the Earth's gravity is more. That's why 1 kilogram will weigh more on Earth as compared to that of Uranus. And the first statement, when you compare 1 kilogram more weight on Venus than Neptune. So when you compare Venus with Neptune, it's opposite. The Neptune is having a stronger gravity that compared to the Venus. And same 1 kilogram weigh more on Mercury than Saturn. So when you compare Mercury with Saturn, so Saturn is having a stronger gravity than a Mercury. So it should be opposite. And Mars and Jupiter. So when you compare mass with Jupiter, it's a big difference. And it will be opposite. So option B is the right answer for this. The next question, on Earth, the gravitational field strength is 10 Newton per kilogram. Means if we have 1 kilogram object, it will experience 10 Newton. Which of these is a value for gravitational field strength on the Mars? So you have to study the table. You have to study the table. We want to compare the gravitational field strength of the Earth with the Mars. So if that is 10, you can see it should be less. So option C and D can never be an answer because C and D can never be an answer. Which of these values? Yeah, C and D can be an answer, not never. The reason is that because there's a value of gravitational field strength. So when you compare this, if this was 1 and this is 0.4, but this is a comparison. Like on Earth, actually, the correct answer for this one will be C, not B. Why? Because when we compare the ratio of the gravity with Earth and the Mars, the ratio of the gravity is 1:, like if this was 1, this is 0.4. So 1:0.4 is a ratio of the gravity, like comparison. So if Earth is 10, how much is the Mars? That is X. So we cross multiply. When we cross multiply, so 0.4 into 10, that's equal to 4 Newton per kilogram. So ratio is 1:0.4, but the value of the gravity is 4. So C will be the right answer. It cannot be D because D is much more than the Earth gravity. Is it clear, this one? Or should I repeat?
Yes, sir, clear.
Because this bar chart is giving it's not giving the value, it's giving a ratio between the gravitational field strength. So the ratio of the gravity on Earth compared to that on the Mars is 0.4. So when you compare Earth with Mars, the ratio is 1:0.4. So if Earth gravity is 10, the Mars gravity will be X cross multiply, so it will be 4 Newton for 1 kilogram. That's why C is D cannot be a right answer, because D gravity is much more than the gravity of the Earth. Like it's D, option D is 25, but it should be less than 10. Same way, if I say the Earth gravity is 10, what will the gravity of the Jupiter? So when we compare, like the ratio between Earth and the Jupiter is 1:2.5. So if Earth gravity is 10, then the Jupiter gravity will be X, we cross multiply, so it will be 25. So using a bar chart, you have to work out, multiply by it. Yeah, it will be basically 10 times of, or 2.5 times 10, that will be 25. Then Deimos is a natural satellite of the Mars. So the orbital time period is 1,820 minutes with an orbital speed meter per second. You have to calculate the orbital radius. So example, this is the planet Mars, and there's a natural satellite which is moving around the Mars. So there's a natural satellite is there which is moving around the Mars. We want to determine this radius, orbital radius, which is, you can say R, small r or capital R. Now, whenever object move in a circular path, the formula we have, that speed is equals to distance divided by time. So the orbital speed is, whenever object move in a circular path, the distance is equal to the circumference, so it is 2 pi r. So in place of distance, we can write 2 pi r. Then time is given in minutes. You should always, like, because if speed is meter per second, time should be in second. Speed is in kilometer per hour, the time should be in hour. If speed is in, like example, per minutes, then time should be minute, but it is in second. So we have to convert into seconds. So 60 minutes, we have to convert into second. So what we will do, we'll multiply this by like 1,820 minutes. We have to convert into seconds. So we have to multiply by 60. So the time will be 1,820 times 60. And the speed, the orbital speed is 1,350. So our subject is R, like we want to calculate the R. So how we simplify for R? So 109,200 seconds here. Then we need R. So how to work out the R? R is a subject. So this will be 1,350 times 1,820 times 60. And this 2 pi is multiplied, other side will be divided. So it will be 3.1. So when we divide this will give us the distance. What's the final answer? 1,350 times 1,820 times 60 divided by 2 into 3.1. What's the final answer for this?
Mister, it's over 2 multiply 3.1.
3.14. The pi. So what's the final answer for the radius, orbital radius? So whenever the number is big, you can represent an exponent. Like this is the final answer. So we have point here 1, 2, 3, 4, 5, 6, 7. Till 7 if I move, so then I will say 23 into 10 to the power 7. And the unit, because the speed was in meter per second, then it will be meter. If the speed was in kilometer per hour, then the final answer will be in kilometer. Then I have to convert the time from minutes to hours. Is it clear, this one? That how we worked out the speed, how we work out the orbital radius from the speed and the time period? Anyone having a doubt or a question in this?
No, sir, clear.
How it got divided by 2 pi? Look, the question is, we have the speed is equals to distance divided by time. The speed is 1,350. The distance is equals to 2 pi r, because it's whenever object move in a circular path, and the time is 1,820 minutes. So we have to multiply by 60. Now we want to find r. So this 2 pi is multiplied with r. So other side it should be divided. That's why it will be 1,350 divided by 2 pi. And same thing. Same thing, if we have, so this 2 pi is multiplied, that's why it is divided there. And 1,820 times 60 divided with r, so it is multiplied. That's why it is 1,820 times 60. That will give the value for r. And then, so this 1,350, 1,820 times 60 divided by 2, and the value of the pi is 3.14. That's why we write 3.14. That's how we got 2 into 3.14 in the denominator. The diagram shows Deimos in orbit of the Mars. Which arrow shows the direction of the force of gravity that the Mars exerts? Now, the value of the pi, you can use 3.14. It does not make difference. Or you can use a calculator pi value. That is also fine. So which arrow is representing the direction? You can use the screen annotation to complete this. So which arrow is representing the force of the gravity, which experienced by this satellite? So the correct answer is A, because that is the force, as this is moving in a circular path. So the direction of the force should always be towards the center at any point. And that is the direction of the gravitational force. In question 5, the moon orbits the earth. State difference between the orbit of the moon and the orbit of the planet. Like how the orbit of the moon is different from orbit of the planets. So how they're different?
The orbit of the moon has less diameter.
Okay. What
and
else?
Also less gravitational force.
Okay. What is the main difference between the orbit of the moon and the orbit of the planet? Size of orbit is one difference. That is fine. But what else? The big difference is there. No, in terms of ellipse, less elliptical, planets more elliptical, that's fine. That is one. But there is a one main difference between the orbit of the moon and the orbit of the planet. The main difference is the moon orbits the planet, where planets orbit the sun or the star. So the center of their path, for moon, it's always a planet. And for planets, it's always a star or a sun. That's the main difference. That's why, like example, we don't say Earth is a moon. We say Earth is a planet. So what is the definition for that? Because the planets orbit a specific star, or moon orbit the planets. That's the main difference between. So the question is not about the size or elliptical. These are fine. But the main basic difference between the moon and the planet, you have to basically distinguish that moon orbits the planet, where planets orbit the stars or the sun. So they ask the major difference that the moon is orbit the planets, or a planet, basically not planets, and the planet orbit the star, or in this case we call our sun, but its main like general term is a star. The sun is a star. The next one, the radius of the moon orbit. The next question, like example, this is our Earth, and this is a moon. The radius of this orbit is given in kilometer, which is 385,000 kilometers. So 385,000 kilometer is a radius of this orbit. It takes 25 days to complete one orbit. We have to calculate the orbital speed of the moon, like what speed the moon is moving. So suitable unit means your unit can be meter per second, your unit can be kilometer per second, your unit can be kilometer per hour, depending on how you want to represent. It's up to you. Like even it can be per day also, kilometer per day. If you don't convert the days, like example 27 days, if you don't convert into the minutes or hours, it can be kilometer per hour as well, but answer will be different for each. So how to work out? Because they did not specify, just the question is give a suitable unit. So the unit, it's just what you represent. So we have the formula that speed is equals to distance divided by time. When object move in a circular path, distance is 2 pi r, and the time is t here, like it will be 2 into 3.14 times the radius. So if I'm not converting the kilometer, so it will be 385,000. And I did not convert the time from days. Your time in second also fine. That's also fine. Like you can convert into second. But what if I'm not converting? If I'm not converting, I'll write 27. So when I write 27, it will be 90,000 kilometer per day. Like when I solve this, it is about 89,600 kilometer per day, or 90,000 kilometer per day. If I did not convert, if I convert the time, it has different speed. For if in kilometer per day, it will be about 89,600. If my answer is in kilometer per hour, then it is about 3,731. If my time is in minutes, it's about 62 kilometers every minute the moon covers. And if it is in meter per second, so it's about 1 kilometer per second. That's right. Like 1.036 is about 1 kilometer per second. So different answers are there. It's better you should know there's a speed. I'm not saying memorize, it's just an information. So you should know, because if a question is calculate the orbital speed of the moon, so as it's not changing, you will remember the answer. So you will have an idea whether your answer is correct or no. So I will write all the values. It depends on what unit you represent. If it is in kilometer per day, then this will be the answer. It is 3,731 kilometer per hour. It is 62 kilometer per minute. It is 1,000 1.04 kilometer per second. That's if you round off to 3 significant, so 1.04 kilometer per second. In question 6, the table shows some data about the planets in our solar system. You don't have to memorize these values. It's too big, too different variable data. You should be able to analyze. Analyze means, like in exam, you will have the table and you have to analyze the table and work out the pattern, or either sometime you have to write a missing value, orbital speeds, orbital time periods, or radius by using a formula. Use the data from the table and answer these questions. So as you can see, you just have to analyze the data and answer the question. Which planet has about the same diameter as of Earth? You can use the screen annotation to do this. You can circle on. So which planet is having the same diameter as the Earth, the size as the Earth? So as you analyze the data, it's Venus. You can see the two values are very close. That's correct. Jupiter has the largest gravitational field strength. Suggest a reason for this. So you have to use the data and say why Jupiter is having the highest, strongest gravity. What is the reason for that? Which column I should select to relate the strength of a gravity? Which one? Diameter, distance, time of the orbiter. So I should compare the mass, not diameter. Like mass and size both are there, but mass is the main factor, not distance. The gravity of the planet depends on its mass. How much matter is there? Or you can relate matter, or you can, so the main thing is the matter, amount of the matter, like how much mass is there. So the answer here, you will refer that Jupiter is having the greater mass compared to other planets. That's why it has the strongest gravity. So gravity of the planet is proportional to the mass of the planet. So answer, because it has a bigger mass, that's why strong gravity. So whenever you compare the gravitational field strength of the planets, you always compare the mass of the planet. State the equation which link the density, mass, and volume. How we can relate the density, mass, and volume? So we have studied in the block 1, the density is mass over volume. This is a Greek alphabet. So you can also write the word equation that density is equals to mass by volume. Calculate the density of a Neptune in kilogram per kilometer cube. So volume is in kilometer cube, and you may assume that the Neptune is a perfect sphere and the volume of sphere is given by 4/3 pi r cube. So we have to calculate the density of the Neptune. Again, you have to use a table. So this is the information which we have to use. We have the Neptune. Diameter of a Neptune is given. Using a diameter, we can work out its radius. And from radius, we'll work out its volume 4/3 pi r cube. And the mass is 100 into 10 to the power 24. So to work out the density, which is mass by volume, we have the mass, which is 100 into, don't forget to write, because in kilogram, it is 100 into 10 to the power 24. Divided by the volume. How to work out the volume? We consider this as a sphere, so volume of a sphere is 4/3 pi r cube. That's a formula to calculate the volume. So it is 4 into 3.14 into the radius. This is a diameter. So what will be the radius? If diameter is 50,000, what will be the radius?
So it will be 25,000.
So it will be 25,000 cube divided by 3. When you solve this, what's the final answer for the volume? Why 10 to the power? Because it's written here, the unit you can see, the mass of the planet is given in 10 power 24 kilogram. So it's 100 into 10 power 24. This is 87 into 10 power 24. It's given in the table that the mass is like 100, then exponent 10 power 24. What is the volume of the Neptune?
104,666.
Okay.
sir, it give me 104 multiply 10 power 3.
And what about others? You can type, can you type your answer in the chat so I'll compare the values? The density of the Neptune. And what about others? Is it same or different for others? Yeah, actually, it's basically the same value. Like, so it is 104,666. And then 100 exponent 24 divided by 104,666. What's the density of the Neptune? When you divide, the reason why
9.5.
yeah,
9.55 multiply 10 power 20.
can you check again because it does not look correct? Yeah, what's the answer for this? Can you check? Because it's like 100 exponent 24 divided by 104,666.
9.5 multiplied by 10 to the power of 20.
Same. So,
Yes.
okay, just a minute, I will check. So it was, when we work out the density, it is 4 by 3 pi r cube. So it is 4 into 3.14 times the radius, which is 25,000 cube, divided by 3. So the volume, it was 25,000 raised to power 3 times 3.14 times 4, then that is divided by 3. So this was 6.5, exponent 13 was it. So 6.54 into 10 to the power 13, that was the volume. And then to get the density, because it was cube, 25,000 cube was it. To get the density is mass over volume. The mass was 100 exponent 24. So it is 100 exponent 24 divided by the previous answer. That is equals to 1.5. So density is equals to 1.52 into 10 to the power 12 kilogram per kilometer cube. Is it clear?
Yes, sir, clear.
So the density is 1.5 into 10 to the power 12. Calculate the orbital speed of the Earth in kilometer per second. Now we have to calculate the orbital speed of the Earth. So to calculate, because Earth is moving around the sun, so we have to use the distance between the sun and the Earth to calculate its orbital speed. So we need orbit. We don't need radius of the Earth. We need the orbital radius of the Earth. There is a difference between radius of the Earth and orbital radius of Earth. Radius of the Earth means like the size of Earth divide, like the diameter of Earth divided by 2. But we need orbital radius We need this. So V is equals to 2 pi r divided by t. And time, because Earth is taking like in the total 365 days, or will convert into. So here, which information? So we need a distance from sun to Earth. That distance is actually the radius, because distance between sun and Earth is a radius of this orbital. So which is 115 to 10 power 6 kilometer. And the time for orbit in Earth days, like it's 365 days. So we'll convert into first into like days into hours, then into minutes, and then into seconds. So it is 115 to 10 power 6. So orbital speed, which is 2 pi r divided by t. And remember the distance between sun and Earth, that is given. So it will be 2 into 3.14 times the distance between sun and Earth is the radius of the orbit, which is 115 to 10 power 6. Divided by, this will be in kilometer, and divided by 365, which is days, we convert into hours by multiplying by 24. Then we multiply by 60 again to convert into minutes. We multiply by 60 to convert into second. So when we do this, it will be about 29.9 kilometer per second. So Earth is moving about, this many seconds, and you just divide kilometer with second, you get kilometer per second. It's better when you're solving an exam, because this will result in large numbers. So it's better when you're solving, you first find the this is when you multiply them, this is 2 pi r, like it will give a total distance covered by the Earth, not the orbital radius. This 2 pi r is a circumference. So when you multiply them, so better solve the numerator separate and denominator separate, and at the last write the answer. Like when we solve the numerator, this is the value. Then we solve the denominator. So when we solve the denominator, then this is the value. And then when you divide them, so it's better, don't try to solve all together, like just putting the values in a calculator and try to get the answer for one step. Because likely in a calculator, like multiplication, division, like it's following like division, then multiplication, addition, subtraction rule. So you may did a mistake if you did not put a bracket on the correct position. So better solve the numerator then the denominator. So 29.870 kilometer. Write your answer in 3 significant figures. So it was 29.870. So that's why I wrote 29.9. Then in part E, a student says that the smaller planets, the shorter its period. Use the data from the table to evaluate this statement. So use the data from a table to evaluate this statement. Student is saying that if the smaller planet, the shorter its orbital period. So you have to compare the size of the planet with the orbital period. Like time to orbit compared to Earth, this table, and the size of the planet. Is there a relation? Can you relate the size of the planet with the orbital period directly, inversely?
Sir, at first it's directly, and then after Jupiter, it's inversely.
So actually, there is no direct correlation. The idea is that when you analyze this data, you find some are following, some are not following. So there is no direct correlation here. because the part here, when you see the statement of a student says, the smaller the planet, the shorter its period of orbit. Like it will take short time. So when you try to evaluate this, the diameter of the planet, like because this is the size of the planet, and this is the time in Earth days or Earth years to orbit. So when I compare the size of the planet, like example, yeah, that's why it is an open response question. It's not like you can say direct or inverse. You just identify the time period and compare whether it appeared to be right or wrong with reference to the planets you choose. But there is no direct correlation. It's not like you say a small planets will take short time, and it's mainly not about the size of the planet. It depends on the distance between the planet and the sun, like the orbital. So size does not have any direct relation with, like some planets, as you see, which is the smallest one here, the Mercury is the smallest one. It was taking 88 days. When I compare the Mars, so when I compare Mercury and Mars, as the size is increasing, the time it is taking longer time. But another planet, like example, when we compare Earth with Mars, so Earth size is bigger, but it is taking shorter time. So the correct answer for this, there is no direct correlation between the diameter or a size of a planet and the orbital time. Some planets have a smaller size, may take longer time. Some planets have a large size or bigger size, may take a short time. So the correct answer for this statement, for this question is, there is no direct correlation between. So there is no direct correlation between the size of the planet and the orbital time. The orbital time, according to the data, the orbital time depends on distance between the planet and sun. And you can, whenever a question is there, so size of the planet is not having much effect on it. And use the data to confirm the statement, like because whenever they say use the data from the table, so I have to use the values to justify my statement that there's no relation, direct correlation between the size of a planet and orbital time. Yeah, it depends on inertia too, but your answer should be very simple. You don't have to use inertia here, as you're analyzing a table. So when you analyze a table, the size of the planet does not affect its time period.